Welcome to the Greek Ship Corrosion channel. My name is Maryam Ehtishamzadeh. I'm a researcher in the field of corrosion and protection of materials. Chapter 2, Section 9, Thermodynamics of Electrochemical Reactions. In this video, Insoluble-Metal-Salt Electrodes, silver chloride electrode, and mercurous chloride electrode are discussed. The main reference is Fundamentals of Electrochemical Corrosion, ASM International. Insoluble metal salt electrodes are constructed for any metal with its insoluble metal salt dipped in a solution containing the common anion of the salt and not the common cation. Obviously, the anion in the solution should come from highly soluble electrolyte. Here is salt bridge that connects the reference electrode to the intended electrode. Here is the construction of a insoluble metal salt electrode. Platinum wire, saturated potassium chloride solution, insoluble metal salt, and the metal. Two important standpoints in insoluble metal salt electrodes. 1. Reference cells for electrochemical measurements are usually metals in contact with solutions containing precipitated metal salt. Number 2. If ions in the corrosive solution can form an insoluble salt with the metal ions that enter the solution as a result of corrosion, the formation of the insoluble salt may have a controlling influence on the corrosion. If the insoluble salt forms as an adherent non-porous film on the metal, corrosion may essentially stop. In these electrodes, the solubility product for the salt is an important consideration. Silver chloride electrode and mercurous chloride electrode are two common insoluble metal salt electrodes that are introduced in this video. Please do not hesitate to put your suggestions in the comments section. Silver chloride electrode. This solubility product for the salt is defined as B moles of AA plus A moles of B minus equals ABBA. Solid precipitate. The product of the activity of the ions, each one raised to the stoichiometric coefficient in the reaction, equals KSP. KSP is a constant known as the solubility product constant. Usually, the concentration of BB minus ions is either known or can be estimated. By substituting in the above equation, metal ion concentration is calculated. Consider Ag plus electron equals Ag. Standard potential of this half cell equals positive 799 millivolts versus standard hydrogen electrode. According to the Nernst equation, non-standard potential of this half cell equals 799 plus 59 times logarithm of the activity of silver cation. If silver cation's activity established by 1 molar chloride concentration in potassium chloride solution and the activity coefficient equals 0.66 and the solubility product constant of silver chloride equals 1.56 times 10 to the negative power of 10, then the activity of silver cation equals 1.56 times 10 to the negative power of 10 divided by the activity of chloride anion equals 1.56 times 10 to the negative power of 10 divided by 0.66. Non-standard potential of silver cation equals 799 plus 59 times logarithm of 1.56 times 10 to the negative power of 10 over 0.66 equals positive 231 millivolts versus standard hydrogen electrode. In the present example, the chloride anion is the variable and the standard half cell potential is that which results for the unit activity of chloride anion. Therefore, the non-standard potential of silver-silver cation equals 799 plus 59 times logarithm of 1.56 times 10 to the negative power of 10 over 1 equals positive 222 millivolts versus standard hydrogen electrode. That is defined as the standard potential of the half cell containing silver, silver chloride, chloride anion. This standard half cell potential is seen to apply to the reaction Ag plus Cl minus equals AgCl plus electrode. If the chloride anion activity is the variable controlling the potential, then the half cell potential is E prime equals E naught or standard potential plus 59 times logarithm of 1 over the activity of chloride anion at temperature of 298 Kelvin. Silver-silver chloride electrode potential in different potassium chloride solutions. In this electrode, reactions are Ag equals Ag plus electron and Ag plus Cl minus equals AgCl plus electron. In saturated potassium chloride, the potential equals positive 196 millivolts versus SHE. In one normal potassium chloride, the potential of the electrode equals positive 234 millivolts versus SHE. And in the solution of 1/10 normal potassium chloride, the potential of the electrode equals positive 289 millivolts versus SHE. The standard potential of the first reaction equals positive 799 millivolts versus SHE, and as it was calculated in the previous slides, the non-standard potential of silver-silver cation half cell equals the standard potential of silver-silver chloride chloride anion half cell. Mercury mercurous chloride or Calomel electrode. A Calomel electrode is a common reference electrode used in electrochemical measurements. Its main function is to provide a stable reference potential for comparison and calibration of potentials in the solution to be measured. The Calomel electrode is made up of a mercury mercurous chloride electrode in contact with a solution of potassium chloride. It can be represented as Hg, Hg2Cl2, KCl at different concentrations of KCl, potassium chloride. The electrode reaction is mercurous chloride plus 2 electrons equals mercury plus chloride anions. Calomel electrode potential at different concentrations of potassium chloride solutions. The reactions in this electrode are 2Hg equals Hg2 2 plus 2 electrons and 2Hg plus 2 Cl minus equals Hg2Cl2 plus 2 electrons. In saturated potassium chloride, the potential of mercury mercurous chloride or Calomel electrode is equal to positive 241 millivolts versus SHE. In one normal potassium chloride, the potential equals positive 280 millivolts versus SHE. In 1/10 normal potassium chloride solution, the potential of the Calomel electrode is positive 334 millivolts versus standard hydrogen electrode. The standard potential of mercury half cell equals positive 796 millivolts versus SHE. The solubility product of Calomel is 1.2 times 10 to the negative power of 18. The product of the concentration of Hg22 plus and Cl minus, each one raised to the stoichiometric coefficient in the precipitation reaction. Thank you for your time. Challenge number 18. If you like to challenge yourself, please answer this question in the comments below. Calculate the standard potential of saturated Calomel electrode using the following half-cell reactions and the solubility product of Calomel. Calomel is a metal insoluble metal salt electrode. 2Hg plus 2Cl minus equals Hg2Cl2 plus 2 electrons. Hg2 2 plus 2 electrons equals 2Hg. Standard potential of this half cell equals positive 796 millivolts versus SHE. And Hg2 2 plus 2 Cl minus equals Hg2Cl2 solid. The solubility product constant for mercurous chloride is equal to 1.2 times 10 to the negative power of 18.